This diagram illustrates natural language processing, or NLP. It is the specific domain of artificial intelligence engineered to bridge the gap between machine logic and human communication. Standard algorithms operate on a strict set of rules. They require highly organized, numerical datasets to function properly. But human communication is a chaotic reality of unformatted text strings and voice data. We speak in idioms, slang, and fragments. Our language is inherently ambiguous and lacks the strict mathematical structure that a processor relies on to execute commands. To comprehend language, an AI system cannot simply absorb it. It has to force this linguistic data through a rigorous transformation pipeline, systematically stripping raw text down into structured, mathematically usable patterns. The machine is not reading in a biological sense. It is executing a mechanical process of data transformation. This transformation happens through a discrete four-stage sequential pipeline. Consider a simple, ambiguous test sentence. The player brought a bat to the game. To figure out what that means, the system will push the text through four impending stages: pre-processing, syntactic analysis, semantics, and deep learning. This complex, multi-stage engineering feat has to execute flawlessly in the few milliseconds between your query and the machine's response. The first stage is data pre-processing. A system cannot ingest our test sentence as a single, uninterrupted block of data. It has to be physically dismantled. The pipeline initiates tokenization. It fractures the sentence into discrete, individual word units. Next, it strips away grammatical noise. Punctuation marks are vital for human readers, but a computer will misinterpret a period or a comma as a unique beta value, so they are purged. All remaining text is forced into lowercase. This prevents the algorithm from misclassifying identical words as different entities simply due to capitalization. Finally, the tokens undergo stemming. The system slices off suffixes to reduce words to their fundamental root forms, consolidating the data. Data pre-processing is an act of destruction. It strips away human nuance to leave behind only the raw computational units of language. Now we enter the second stage, syntactic analysis. On their own, these isolated tokens still lack relational value. The machine has a list of words, but no instructions on how they interact. The system evaluates the token arrangement to establish strict grammatical relationships, snapping the units together into a syntax tree. By mapping subjects to verbs and verbs to objects, the algorithm creates a structural blueprint of the sentence. This structural mapping is the critical prerequisite for understanding. Without syntax, the machine has data, but absolutely no framework to interpret it. The third stage is semantic analysis. The pipeline has a perfect grammatical blueprint, but syntax cannot resolve contextual ambiguity. The issue is that human words possess multiple, conflicting definitions, depending entirely on the speaker's intent. To solve this, the pipeline deploys a mathematical mechanism called word sense disambiguation. Take our token bat. Does it mean a flying mammal or a wooden club? The algorithm scans the surrounding tokens. It calculates the probability of a flying mammal appearing in the same context as the tokens player and game. The math points overwhelmingly to the other option, locking in the correct contextual path. Semantic analysis is the exact moment where cold computational data is translated into human intent. The final stage is deep learning. Here, the structured, defined tokens are fully ingested into a neural network. Rather than just looking at local sentence structure, these models rely on training drawn from massive global datasets. The network detects complex, non-literal patterns across millions of examples, allowing it to interpret overarching sentiment, sarcasm, and broader context. Deep learning is the engine that elevates rigid grammatical parsing into nuanced, adaptable machine comprehension. Zooming out from the internal architecture, we can see exactly how this pipeline powers real-world applications. This visual highlights four foundational utilities of NLP that rely entirely on these stages: virtual assistants, chatbots, spam detection, and text summarization. When you speak a command or type a customer service inquiry, virtual assistants and chatbots execute this entire pipeline instantly to interpret your need and generate an accurate response. Spam detection heavily utilizes semantic analysis to identify hidden malicious intent within seemingly normal emails, filtering out threats before you even see them. And live translation requires this pipeline to function simultaneously across multiple conflicting language models to maintain the speaker's original meaning. Every seamless, automated communication interface in the modern world is dependent on this underlying architecture. Ultimately, artificial intelligence does not read language in any way that a human would recognize. It is executing a sequence, cleaning the data, structuring the syntax, defining the semantics, and mapping patterns via deep learning. Natural language processing is a profound data engineering triumph. It successfully forces the chaos of human expression into the unforgiving logic of computation.